Hi, this is Ashim Datta. I'm in the Department of Biological and Environmental Engineering at Cornell University, and this is a short video in a series of short videos that are meant to recap the math needed for undergraduate heat conduction or diffusion course. And this is the simplest, absolutely the simplest situation where we're talking about homogeneous equation in Cartesian coordinate. In other words, we're talking about solving uh, this equation, which is, of course, uh, nearly trivial for the boundary condition of value given, which is also called the Dirichlet condition. So this is the equation we are trying to solve here. Notice that this equation is second order and it is homogeneous because the right hand side is equal to 0. So here t is a function of one variable. So if t is a function of one variable, I can write this as simply d squared t dx squared equal to 0. Now we can solve this easily. This is the simplest case that we will ever do in our heat transfer class. So let's solve this one. So we can think of it this way. We don't have to think about all of this, but to get started, maybe we can think of it this way. So d dx of something equal to 0. So this is my function, let's say. So if the derivative is equal to 0, then the function must be a constant. So let's call that C1, where C1 is a constant. And then if we repeat the integration, then we get t equal to C1x plus C2, where C2 is also constant. And by constant, we also mean they're unknown. Okay, so they are unknown. Now this C1 and C2, so C1 and C2 need to be solved for. Okay, so even though we have a solution for the differential equation, it is really what's called a general solution. It tells us, and let's plot this. So suppose so this equation simply tells us that temperature T, or the y, is a linear function of x. But this is not enough to know the exact value of T at a position until we find C1 and C2. So what we need is what's called a particular solution. So we need a particular solution by solving for C1 and C2. Okay, and so how we get this is we called or what we need for this is we need the boundary conditions. We need boundary conditions. So these are additional conditions to solve for C1 and C2. So the simplest type of boundary conditions, boundary conditions can be T at x equal to 0 is equal to T1. So what is T1? This is a value given. Okay, so for this class, for the purpose of this class, it is typically a constant, but it doesn't have to be. It can be function of some other variable like time. A constant. Okay, so in this plot, then at x equal to 0, I'm given T1, and then likewise T at x equal to L is T2, another value given, again typically a constant. So at x equal to 0 it's T2. Okay, so with these two additional conditions, I can now solve for C1 and C2. So using the first boundary condition, I get, what do I get? T1 is equal to C1 times 0 plus C2, which gives me C2 equal to T1. And then using the second boundary condition, we get T2 equal to C1 times L plus C2. So C1 is equal to T2 minus C2 over L, but C2 is already known, so this is equal to T2 minus T1 over L. So now C1 and C2 both are known, so we plug in C1 and C2 into this equation to get the final solution. T is equal to T2 minus T1 over L times x plus T1. So this is our particular solution, and from here we can actually get temperature at one point. So this solution plotted would look like this, and so now we know the exact equation. At any point we can find the temperature or the value. So you notice that this T2 and T1, there are some given constant. So this whole thing is known, and then T1 again here is known. So this is absolutely the simplest situation, and we're not typically going to have more complex situation than this, but for this simple condition, that is for a Cartesian geometry 1D Cartesian, so where you have a temperature given or the value given in one end and the value given in other end, the solution is a straight line. Thank you.